Hey folks, today we're going to learn about the derivatives of inverse trig functions. So let's get right to it. The first part that you're supposed to be doing is just filling out this table, listing the 6 trig functions of which you're familiar with, the inverse trig function, sorry. So we're just going to go ahead and list these out just so we can have them. So sine inverse, cosine inverse, tangent inverse. What else do we have? Well, 1 over sine, that'd be cosecant inverse of x, right? Secant inverse of x, and then cotangent inverse of x. All right? Okay, so that's just prior knowledge that you'll need. List the 3 trig Pythagorean identities below. This will be the main one that you will need to know. Sine squared x plus cosine squared x equals 1. And then to get the other identities, all you need to do is divide by sine and then divide by cosine. So let's divide both sides by sine, that sine squared, and that'll give me cosine squared divided by sine squared will be cotangent squared. And 1 divided by the sine squared. 1 over sine squared cosecant squared, right? Is cosecant squared x. Okay. So the next thing we'll do is we'll divide everything by cosine. Well, sine over cosine is tangent, so sine squared over cosine squared is tangent squared. We're just still dividing by cosine squared, so that'll be 1. And if we divide this one by cosine squared, that'll give me secant squared. Okay? So those are your 3 trig identities that you may need and refer back to. Okay, so now consider that we may want to find the derivative of the function, something like y equals sine inverse x. Okay, however, we don't want have a rule yet for doing that computation. So what we have to do is kind of, here, I'm just going to write this. I'm going to write it as sine y equals x. And what you're really doing is you're taking the sine of the left-hand side of the equal sign, and you're taking the sine of the entire right-hand side of the equal sign. Well, if you know the relationship between inverse functions, you know that if I plug in an inverse function to its inverse, right, then that result is actually going to give me x. And we've talked about this a number of times, how if you plug in an inverse function into its original function, then, or if you have 2 functions that are inverses of each other and you substitute in one inside the other one, that result will be x. So that's exactly what we did to get sine y equals x. Okay? Thought you might need a little bit of help on getting to that step. So anyway, using implicit differentiation, so we're going to take the derivative of both sides. So sine turns into cosine y. But remember that y is not the variable x, and we're doing the ddx of both sides. Okay? So we're doing it in terms of x. So we need to have an extra chain rule factor here, dy dx. And we're taking the derivative of x, and that'll just give me 1. So to solve for dy dx, we're going to divide by cosine y. Okay, and then the Pythagorean theorem, Pythagorean identity above. Okay, so cosine y. Well, if this was to say cosine squared y, then I could solve for that, right? So cosine y, let's see, I would have 1, and I would subtract sine squared y, but then I'd have to get rid of that squared, so I'd have a square root here. Okay, so cosine y is actually the same thing as 1 minus sine squared y. So, dy dx equals 1 over 1 minus square root of 1 minus sine squared y. Now, there was a typo in my notes, and I made a note to change it, and then I never changed it. So I want this to say sine y equals x, and therefore sine squared y equals x squared. Okay. Sorry about that. So anyway, we have sine y equals x. Now, where did we get that? Well, sine y equals x from our problem. Okay, so we know that. So I'm going to go back and substitute again, and instead of writing sine squared, I'm going to write x squared. So 1 minus x squared. Okay? So that is the derivative of sine inverse of x. Okay? Now, a typical derivative problem involving an inverse trig function also involves the chain rule. So you're typically not going to take the derivative of sine inverse x. It'll probably be sine inverse of, let's say, 3x squared. All right, so the tip is to let u equal the inside function, and that inside function will be a function of x. Okay, so I'm just going to add that note. It's going to be a function of x. So, and apply that chain rule to it. So, then substitute it back into your expression in terms of x. So, I don't care to show you guys this notation anymore. I thought that it would be helpful, and I think that this is the most helpful way to kind of memorize what we're doing here. So, we're taking the derivative of sine inverse of u. Well, we just substitute in u instead of x right there. And then we need to take we're basically using the chain rule. It kind of looks like implicit differentiation, okay, but we'll be taking the derivative of whatever that inside function is. All right, so here goes our first couple of practice problems. We'll find the derivative of y. It says sine inverse, so I know it's this formula, 1 over square root 1 minus whatever's on the inside there. So let's call it x cubed, but we have to square that. And then we'll take the derivative of x cubed, and that's 3x squared. And you know what? Simplifying it, you can do that. I'm just going to leave it right now. Okay. Find the derivative of the next question. Well, dy dx equals 1 over the square root of, so it's the same formula. We just need to get used to using it. Now this one's strange. It's the square root of x squared, right? Now you have to have memorized the derivative of the square root of x. Well, the derivative of the square root of x is 1 over 2 square root x. So again, this one I could make this look better. Okay, I could make it as one fraction, put the 2 in front, all that good stuff, but I'm going to leave it there because typically if you want to go any farther, you can just put a number in. So if I wanted to evaluate sine inverse at, or the derivative at 4, I can substitute in a 4 there and find out what that number is. Okay, so this says to follow similar steps to the previous page to find the derivative of y equals cosine inverse x. Well, let's do that. Well, I'm going to take the cosine of both sides so that I have cosine y equals cosine of cosine inverse x. And of course, if I took the cosine of cosine inverse, then that would result in just the input, x. Okay, so cosine y equals x. I'll take the derivative of both sides, the d dx of both sides. Well, that's going to be negative sine y, but remember I'm taking the derivative of this function of y, so I need to do a chain rule, dy dx. And the derivative of x is just 1. I'll solve for dy dx by dividing by negative sine y. And then I'll try to figure out what negative sine y is by using that Pythagorean identity. I'm also going to put the negative 1 in the numerator. So now, what would sine y look like? Well, sine y, if you go back and solve that Pythagorean identity, let's see, sine squared equals 1 minus cosine squared. So let's see, sine y would equal 1 minus, or square root of 1 minus cosine squared y, right? Now by substitution, we know that cosine y equals x. We set it up here, that cosine y equals x. So that's just going to say x squared. So negative 1 over the square root of 1 minus x squared. And that would be the derivative of cosine inverse x. Now, did you expect this? The only difference is the sign, right? The symbol. And did you expect that symbol change? Maybe you did. Okay? Maybe you should have. Maybe you look at it now and you say, oh yeah, okay, I know why. Now, remember that we decided that anytime we have the letter co in front of it, we're taking a derivative of something co, we're going to have a sign change. Okay? So there you go. So this says to write the formula for the following, the derivative of cosine inverse of u, where u is some function of x. Okay? So u is some function of x. So that just means that we're going to have to apply the chain rule. So here we go. Same formula. 1 minus u squared times the derivative of that inside function. The inside function in this case is just u. Okay? So, let's go and do a couple of examples. So the derivative of cosine inverse of 3x to the fifth is just going to be negative 1 over 1 minus whatever it is in the parentheses. So 3x to the fifth, and then we square it. Then we take the derivative of what's inside, and that's 15x to the fourth. And while I can make that look a little bit nicer, it wouldn't look much nicer. I would just put a negative 15 on top of the numerator instead of multiplying it out like this. And I might do 9 for 3 squared x to the 10th on the denominator. So if you have a multiple choice question, yes, you can simplify. But let's move to the next example. dy dx equals, this time negative 1 over the square root of 1 minus all that squared. Well, that's just 2x. And then we take the derivative of 2x. All right, so I hope that's simple enough. What we see now in the next statement is that I'm just going to give you the formula to tangent inverse. Now, it's the easiest formula to remember. It might be the hardest proof to follow, so we're not going to really get into that proof. But let's write the formula for tangent inverse if there was a u instead of an x. So it would be 1 over u squared plus 1 times the derivative of u based on in terms of x, right? So let's go ahead and do a couple of questions. So here we go, tan inverse. So dy dx equals 1 over 4x squared plus 1 times the derivative of the inside function. Well, that'll be 4. Next question, dy dx equals 1 over 5x to the third squared plus 1 times the derivative of the inside function. Well, that'll be 15x squared. That is how simple it is. Now the hard part is just having these formulas. Okay, so when you go to the next page, you will be overwhelmed, maybe. Here are the inverse trig functions, and all of these just have an input of x. All right, so you can memorize those formulas, but for sine of, but typically we don't have just an x in there. We're typically going to have to apply this chain rule factor to all of this. Okay, so the most heavily tested are going to be sine, cosine, and tangent. I had seen sine 3 times as likely, tangent 2 times as likely, and then cosine inverse would be, you know, I would see the problems in that proportion, 3 to 2 to 1. I very rarely see a secant inverse problem. I've never seen one on the AP exam. However, they do show up on some people's homework exercises. So just have this list available to you, even if the whole thing is not memorized. Only memorize the ones that I've starred there for you. In each case, the derivative of the inverse trig function with the word co is just the negative of the derivative of the inverse trig function without the co. So really, if you just memorize the first 3, then you have already memorized the other ones, because all you have to do is stick a negative sign out in front. Okay, so what if we did secant inverse? Well, the derivative of f is just f prime, so that's what we're being asked to find. And we're going to use this formula up here. So we'll just make a fraction bar, do 1 over absolute value 5x cubed. That's a neat little thing to think about. This input, if it was something squared, then I wouldn't even need the absolute value, right? But I'm gonna use the absolute value in this case. So here we go, and we're going to say something squared. So I'm not going to square it. I'm just going to put it in parentheses to show people that I'm supposed to be squaring it. Okay, and then actually times du dx. So the derivative of the inside function is just 15x to the 4th. I'm sorry, 15x to the 2nd. So that's how you apply that one. It looks like this one should be a U-try problem because we've already done sine inverse. This problem, though, this is a doozy. Okay, so this is a product rule. And the reason it's a product rule is because I have x squared times cosine inverse. So I'll take the derivative of x squared, and then I'll just write down cosine inverse of 4x squared. But then I need to write down the x squared. Then I'm going to be taking the derivative of cosine inverse. Well, that's negative 1 over the square root of 1 minus u squared. Oh, that u is 4x squared. And then I'm going to need to take the derivative of the inside function. In this case, it's going to be 8x. All right? So there could definitely be some simplifying. I would probably call the final answer, I would say minus 8x cubed over 1 minus, what is that, 16x to the 4th. So I would just fix this second term. The first term looks fine the way it is, 2x cosine inverse 4x squared. So anyway, on a multiple choice test, it might be like that, or it might even have a common denominator. So watch out for that. So here's a derivative, another derivative. So you should notice that the derivative of e to the x and e to the x, if you just write it down, it's always the same thing. So I'm going to do a little trick here. You don't have to do the trick, but it's going to save me a little bit of space. I'm going to write e to the x. I'm factoring it out pretty much, okay? And I'm going to write it as tan inverse of 3x to the 3rd plus, now I need to do the the derivative of it. Get my words switched up. So u squared plus 1, 3x to the 3rd squared plus 1 times the derivative of the inside function. And that's going to be 9x squared. And then we'll close that parentheses. And actually, you know, sometimes I use these brackets. These brackets are they're the same thing as parentheses. It just kind of organizes things a little bit better for me, because if I have a lot of parentheses going around, sometimes the brackets can help me read it a little bit. Okay, guys, I hope that you enjoyed that lesson. I did my best to teach you guys the derivatives of inverse trig functions. If there's any questions that you have, please forward them in my direction, and I will do my very best to help you guys out. Take care. See you on the next video.